Okay, 9.3, we have the two thin film interference equations. So we haven't had the chance to do a lab with this, which is unfortunate. I'm going to hope that maybe you've seen like a sort of rainbow pattern that forms if you have like an oil slick on the road. I'm sure maybe in your driveways you've seen something like that. Um, those patterns, those fringes, the reason they're colored is because white light is reflecting off of a boundary. Like let's say this blue box here is a layer of oil. What happens is some of the light reflects right at the top surface. That becomes A. When light reflects from a higher index of off of a higher index of refraction, it undergoes a phase change by pi. So that's what you see. Some of the light, however, refracts. So that's what you're seeing in red in this schematic. Some of it refracts, and then it reflects off of the bottom surface and refracts again, and it is still in phase with the original wave, assuming maybe this was water and water, there was maybe like a splotch of water down here, and water would have a lower index of refraction than, this could be N1, N2, so N2 would be lower than N1. So it would reflect, and it would remain in phase with the original wave. So if you want to review that, you can go back to the slides that shows the two different ropes, how the wave reflects in that instance. But for A, because the index of refraction of air is so much lower than the index of refraction for oil, the A undergoes a phase change of pi. B stays in phase with the original beam of light. These two different reflections, these two different beams, they're going to interfere with each other. So places where you have constructive interference, you're going to use this equation. You'll see the bright patterns, like rainbow patterns if it's white light. You have to add in this 1/2 because for the constructive interference, for these two to constructively, A and B to constructively interfere, you have to account for the fact that the A beam is out of phase by pi, or half of the wavelength. So if these two beams can reconvene at a place where their path difference is half of a wavelength apart, they're once again in phase. So there is a question on this. And I will discuss that again. And then for thin film destructive interference will happen when they're an n multiple or an m multiple of the wavelengths apart. So when A and B reconvene here, if I don't add in a 1/2, they're phase shifted by pi. They're out of phase with each other by pi, half the wavelength, so they cancel. All right, so for constructive, for the thin film, you have to add back in a 1/2 to find the path difference that puts these two waves back in phase with each other. All right, let's go on and do practice problem number 4, excuse me. Practice problem 4. A thin film of oil of constant thickness floats on the surface of water. The refractive indices N of each material is shown on the diagram. Explain why the film of oil appears to show colored fringes. So just like I explained in the previous slide, the reason there is a colored fringe is because some of the light is reflecting right at the air-oil boundary. When the light reflects from a lower index of refraction off of a higher index of refraction, it undergoes a phase shift by pi. So this wave is now inverted, plus pi. Okay, some of the light, however, gets refracted, and then this light also reflects off of the oil-water boundary. When the water refracts, there's no phase change, and when the water reflects off of a lower index of refraction, like between oil and water, there is no phase change. So it just continues, it continues straight on through. It reflects off, there's no phase change, and then it refracts once again. And then these two waves, the blue and the red, they are going to interfere with each other in air. When you have the colored fringes, that's where they interfere constructively. When there are black fringes or there are dark patterns, that's where you have destructive interference. So for this, you will have to explain the fact that you have constructive interference when the light that reflects off of the air-oil boundary is half a wavelength apart. From the light that reflects off the oil-water boundary. When these two interfere with a path difference of lambda over 2, you'll get constructive interference. So put that into words and we'll go on to part B. When white light is normally incident on the surface of the oil, the film appears green to an observer. The wavelength of green light in air is 520 nanometers. Calculate the thickness of the film of oil. So we get to see this green light. So if it's not a dark patch, then that means that we have constructive interference. So I'll use the equation 2 times the index of refraction of your thicker medium times the thickness of that medium, sorry, not the thicker medium, the target medium, times the thickness, lowercase d, of the medium, is equal to some integer value m plus 1/2 times lambda. Lambda equals 520 e negative 9 meters. N, in this case, is 1.40. That's the index of refraction for oil. In this case, I will let m equal 0. When m equals 0, that's where we have our central maxima. So I'll let m equal 0, and by adding in 1/2, I will now have a bright fringe. So all I'm left to solve for is my unknown d, where d is the thickness of the oil layer. Not too bad. Isolate your unknown and solve. Next up, practice problem number 5. Number 5, a thin film of oil lies on a puddle of water. White light from above shines on the film at normal incidence. Outline the process by which colored fringes are formed. So for this, I want you to explain what happens first to the beam of light that gets reflected at the air-oil boundary. So what happens to the phase as this light is reflected? Then I want you to discuss what happens to the beam of light that gets refracted through the oil and gets reflected at the oil-water boundary. I want you to explain when we have colorful fringes between this beam, which I'm going to label beam A, and this beam, which I will label beam B. Keep the colors consistent, my bad. This is beam A, and this will be beam B. And I want you to explain what has to happen to the path difference such that A and B constructively interfere. Part B, the following data are available. The refractive index of oil is 1.4. The refractive index of water is 1.3, and the thickness of the oil film is 250 nanometers. Calculate the wavelength of the incident light for which destructive interference occurs. So in this case, I will use this equation, 2 times the refractive index of oil times the thickness of oil. That'll be 2.5 e negative 7. I'll set that equal to m times lambda. Now when m is 0, we have a central maxima, or we're at the central maximum. So we're going to let m equal 1, and we have now the first dark fringe where m equals 1. As long as I know where I'm at in the interference pattern, I can easily use these equations. I can easily plug in for an m. Later on, we'll see, in the past, IB used to give more difficult problems where it wasn't quite clear where m would be. So this is not a hard problem. You'll have 2 times 1.4 times 2.5 e negative 7, and that will give you the lambda of light. Coming up next, practice problem number 6. Question number 6. A thin air wedge consists of 2 flat glass plates that form an angle theta of 1 times 10 to the minus 3 radians. When illuminated with monochromatic light from above, the fringe pattern is observed in the reflected light. The distance d between 2 consecutive fringes is 0.30 millimeters. Calculate the wavelength of light. So I will say this: we don't have time to do a thin air wedge interference lab. It's unfortunate. It's a more advanced lab, and it would be really hard for us to see this fringe pattern on the right without a good setup. It would be hard to measure the spacing between them unless we could really amplify the light source. And then we would do subsequent calculations to figure out how far away it is, the image from the screen. It could get pretty complicated. This is something you would do in college. So unfortunately, these questions kind of put students at a disadvantage, and IBO reported that only a handful of students from around the world even got this question right. Since then, I noticed, or question was made in 2014, and I haven't noticed any questions featuring the thin air wedge since 2014, but just in case, because it was very popular from 2014 to 2010, I'm still going to ask you on this, but for the exam, I won't have a question like this. But let's see what happens. So we have light striking these 2 glass plates, and you can see the glass is forming kind of like a ramp. So what happens is the light shines down, it's going to refract through, reflect, and interfere with itself, and what you'll get, what you see from above, will be these fringe patterns, the ones that are displayed on the right. So you're physically able to see this fringe pattern reflected back up at you. We want to figure out the wavelength of light based on the spacing between these fringes, based on the angle of incline, and just using those 2 things. Okay, so I will start by using the thin film interference equation, but I'm going to use the interference equation for destructive interference. And I will choose the center band as my target. Okay, so this center black part occurs when m equals 1. This is my first minimum. So I have 2 times the refractive index of air. By the way, air is the medium here. It's not a fair question, I think. Times d, where d would be the thickness, d would be the maximum separation between the plates. Oh yeah, it's lowercase d. I set this equal to m, where I'm letting m equal 1, times my unknown lambda. The problem is d is also unknown, so I have to relate d to the spacing of the fringes via the small angle approximation. So let's consider d is the space between any of the dark fringes. Okay, so this could be like d between here and here. D would be related to this red d, which I'll redraw this line right there. Lowercase d. These 2 are related to each other by that angle. So it's like a ratio. I can see that this little d kind of forms part of an angle. It makes up one small side of this total angle, of this total side of the triangle. And I know that the lowercase d is the separation between the plates. I'm looking for the lowercase d, so if I treated this like a tangent function, tan theta equals a opposite, which is the lowercase d, what I'm solving for, divided by the adjacent side, which is capital D. Small angles then would say that theta then is little d over d, little d over the big D. So little d, sorry about the bell, is theta times capital D. So I will replace theta times capital D with little d, and then I will solve for lambda. Make sure to convert capital D to 0.3 e negative 3, so that's 3 e negative 4. And N for air is 1. So yeah, this was a harder question, and of course it makes sense why high school students wouldn't get this one right. But I still want you to practice because you never know, just in case. And I'll just follow my steps here and then continue for part B. For part B, it reads, the upper glass plate is now replaced with a curved glass plate. The dotted line represents the upper glass plate used in part A. Sketch the new fringe pattern in the space below. The fringe pattern of A is given for comparison. So once again, IBO stated that practically no one got this right. Maybe a handful of people from around the world. That totally makes sense. You guys, we don't really do thin film interference labs. The only way you would really know how to answer this problem is if you were familiar with Newton's rings. So in like the 1700s, Newton took a curved lens, like I just put up on the screen in blue, and he rested this curved lens against a flat plane of glass, and then he irradiated the flat plane of glass with some light. Okay, so the light was striking this. The light refracts through the lens, obviously. Some of it reflects back. Then the light continues, refracts through the air, and then reflects back on the glass plane. And so he's looking down at this glass, and what he sees back on him is this image. These are called Newton's rings that just popped up on the screen. These rings form due to the interaction between the light that first reflects at the bottom of the curve and the light that refracts through the air and reflects at the flat glass plane. So it's this interaction here that causes this amazing ring pattern, and these are called Newton's rings. And so you can see how the fringe spacing changes. So right when you're really close, when the angle between the curved surface and the flat plane is narrow, or it's a small angle, they're close to each other, the fringes are further apart. You can see this here. These fringe spacings, they're further apart. The closer you are, the closer the curve is to the flat glass plane. As you get further up the curve, the fringe spaces decrease. So there's no way you would know how to do this problem unless you were familiar with the Newton's rings setup. So a lot of people were at a disadvantage for this question. Okay, and the important thing to know is that the number of fringes, if we replace the flat glass plane with a curved surface, the number of fringes doesn't change. So the closer we are to the left-hand side, the new fringe pattern is very spaced apart, and there are it's very, like the spacing is far apart. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 fringes. There should still be 9 fringes. All that's happened is, as you go from left to right, the spacing of the fringes gets smaller and smaller. So 2, 3, 4, 5, 6, 7, 8, 9. I mean, who would know to do this unless you study Newton's rings? Okay, next up, practice number 7. Okay, practice problem number 7 is a type of problem you will actually have on your exam in the class. This is something you can totally do. A thin layer of oil of refractive index 1.5 floats on water of refractive index 1.33. Light of wavelength 579 nanometers is incident normally to the surface. Determine the minimum thickness of the oil that needs to give rise to the least amount of light being reflected. That's where we have destructive interference. So we'll use the equation 2ND equals m times lambda, and I will just assume we're at the first minimum. So m equals 1. 1.51 is the refractive index. Lambda 5.79 e negative 7, and we have, that's it. And so you're then solving for unknown d, lowercase d. Not bad. Follow me for part B. So for part B, it states, describe the change in the intensity of the reflected light as the thickness of the oil layer in A is gradually increased. So initially we had a dark patch, so low intensity. As we increase the thickness, what will happen is we will then get a more intensity. We're changing the path length in this case. So where that spot was, where it was no intensity, then we'll have more intensity. And then as we increase further, the path difference between those beams of light changes again. So then it oscillates and it becomes less intense, and then more intense, and less intense and more intense, because the path length of the waves that are recombining in the air, it's changing. So we have more intensity followed by less intensity and then more intensity, and as you get bigger and bigger, eventually the intensity of the rays just becomes constant. Once you get beyond the thickness, once the thickness of the oil layer is beyond the order of magnitude or of the wavelength, then you don't really see the effect anymore. Intensity becomes constant. Okay, next up, practice problem number 8. So again, we have one of these hard problems, but I'm going to walk you through it. The diagram not to scale represents an experimental setup designed to measure the diameter of a human hair. This is like a college level lab. A hair is used to separate two microscope slides. A monochromatic beam of light is reflected onto the two slides by the glass plate. The light is then reflected from the two slides and is transmitted through the glass plate and is viewed by the traveling microscope. A. State why the light reflected from the two microscope slides produces a system of interference fringes. So just like before, I want you to explain using what I described with the oil-water layers, how the light, some of it gets reflected right at the first glass layer, some of it gets refracted through into the air and gets reflected at the second glass layer. What happens when these two reconvene and they're out of phase by pi versus totally in phase? So that's an acceptable explanation. For part B, the condition that a bright fringe is observed in the field of view of the traveling microscope is given by the relationship 2dn equals m plus 1/2 times lambda, where d is the thickness of the air film formed by the wedge at the point where the bright fringe is observed, m is an integer, and lambda is the wavelength of the incident light. State the reason for the factor 1/2 in the relationship. So for this explanation, I want you to discuss how a wave gets inverted by pi. It's a wave is shifted out of phase by pi when it's reflected, at a boundary where the N1 is less than N2. To account for that inversion, that's why you then have to add in this lambda over 2, or a 1/2 factor. This will allow the two waves to then have the same phase. They will be then in phase with each other. Okay, finally, part C. Okay, part C, and this one is easily the hardest one. In the diagram, the length of the slides is 5 centimeters. The wavelength of the monochromatic light is 592 nanometers. Using the traveling microscope, it is observed that 50 fringes occupy a length of 0.940 centimeters. Show that the diameter of the hair used to separate the slides is about 80 micrometers. So this question comes from 2010, 8 years ago. And this is a real college lab that you will do for optics and physics. You end up separating two glass planes like I've shown, and you'll have some hair or some very small piece of wire. You'll see a pattern of fringes, like interference. It'll reflect back up at you, and these, as long as the glass isn't curved, it will be evenly spaced fringes, just like we saw in the previous problem. The difficulty in this is knowing, first of all, we are going to be using the equation 2ND, where D is the unknown thickness of the hair, equals M times lambda. The difficulty with this is the fact that we don't know what M is, and it's not sufficient to say that M equals 1, like I was able to simplify or do in the previous problem. I can't just say M equals 1 because I have to figure out exactly where M is. I have to use the M that corresponds to where the hair is. This makes this difficult. Not really difficult, but I can't just say M equals 1 or 2 or 3. I have to know where the hair actually is, along which fringe how far from the central maxima the hair is actually placed. So it's tough. So I have to use, it's not that tough, but I mean, you just wouldn't know that unless you did a lab like this before. So I have to figure out what my unknown M value is before I can solve for the unknown D value. So I know that this, the glass slide is 5 centimeters long, okay? And I know that there are 50 fringes that occupy 9.40 centimeters. So I can figure out how many fringes there are along the entire 5 centimeter length by dividing 5.00 centimeters by 0.940 centimeters per 50 fringes. This will tell me essentially the M order, M being the number of fringes, where my hair is at the very end of all this pattern. So 0.940 centimeters over 50 fringes, you will calculate how many fringes there are. You can do 5 divided by 0.94, multiply that by 50. That then becomes the value for M. Plug this in. This is your M value. It should be around 100 or so, or around 200, and then divide by 2. That's why the 2 is there. So dividing this eventually by 2, because we're looking for D, will tell me just how far from the central maxima. Sorry, the central maxima would be a bright spot, so I'll do it in yellow. Just how far from the central maxima the diameter of the hair is. The index of refraction is 1. Lambda I've given you the M value, and all that's left is to solve for D. So even though I'm not going to give you a question like this on the exam, I think this is too hard for a high school level, especially if you haven't done a lab like this. I still just want you to see it. Who knows, maybe just in case you'd have a question like this and this might jog your memory. Thank you for watching. This is due next class.